Hello friends, so once again welcome to my channel MathAlcoholic. So today I'll be discussing from question number 7 onwards of the miscellaneous exercise of the chapter relations and functions, that is the first chapter. So continuing from question number 7, it is given that give examples of two functions f that is defined on natural numbers and also g that is defined on natural numbers such that g of f is onto but f is not onto. So here we need to find such examples where f is not onto and g of f is onto. So you may find it by your own, there is no problem in it, but it would consume time as you would be going for many kind of hit and trial methods. But here, as it's a miscellaneous problem, I purposely give the hints also. It is given that consider fx to be x plus 1 and gx to be x minus 1 and 1 by determining like this. Okay, so we have selected this because g of f will be onto. G of f will be onto. How? Let us see that. Now here we define for the solution, we define why it is not given because clearly it is in the hint. So we define f that is from n to n as f of x is equal to x plus 1. Okay, again we are going by the hint. We define g from n to n as g of x is equal to x minus 1 and 1 if x greater than 1, if x is equal to 1. Okay, so these are the definitions. Now clearly here fx is not onto. Why fx is not onto? Because see, fx is x plus 1. Okay, so you go on putting x, which is natural number, and the output must also be natural numbers. Alright, so see, initially it may seem that it is an onto because if you put any natural number into it, the outcome will be a natural number itself. But if you look at it very carefully, see, there is no x such that f of x is equal to 1 because f of x comes out to be a natural number and every other natural number satisfies a natural number from the domain. But fx is equal to 1 has no x for which it will satisfy. See, for fx equal to 1, x must be equal to 0, and that clearly dissatisfies this relation. So by this context, f is not onto because one element is not related to it. Alright, so see, if I draw a more general diagram, if I draw the mapping from n to n of f, 1, 2, 3, 4 will be elements here of the domain and 1, 2, 3, 4 will be of its codomain. So 1 will be related to x plus 1, 2 will be related to 3 will be related to 4, and this way it will go on. But here in the codomain, see, one element is missed out. The range is 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I think I need not to explain it more than this. So it is clearly not onto. That's why it is given. Now clearly f is not onto as there exists no x in the domain such that f of x is equal to 1, that also belongs to natural number. So f is not onto. Now let us see how g of f turns out to be. Now g of f from n to n is defined as see, g of fx is going to be g of f of x. Okay, and see, g of f of x is going to be g of x plus 1. Alright, so g of x plus 1, check it out that x plus 1 is always greater than or equal to 2. X plus 1 is never 1, so it will be just opening with this x minus 1. Okay, because x plus 1 is never equal to 1, it is always greater than or equal to 2, just because of the same reason why f is not onto. So g of x plus 1 will be giving me only this. So g of x plus 1 will be x plus 1 minus 1 because x plus 1 is always greater than 1, it is never equal to 1. Okay, so clearly that is equal to x, hence g of f x is equal to x for all x belongs to natural numbers. This implies our conclusion this implies for all y belongs to n, there exists an x that is equal to y. X is equal to y because g of x is equal to x. So if you put, means you will be always finding a y. For all y there exists an x that is equal to y belongs to n, such that g of x is equal to y. Therefore we can say that g of is onto. Okay, so I hope this is very clear. Because x and y both belongs to natural number, we can find an x that is equal to y such that g of x means you can assume it to be hx. Okay, so g of x will be equal to y for x equal to y, and that belongs to n obviously. So g of is onto. Okay, I hope you have no doubt. If you have any doubt, please feel free to use the comment section. Coming to the next question. This question is a very easy question once again. Given a non-empty set x is a non-empty set. Okay, x is a non-empty set. Consider P of x, which is the set of all subsets of x. Okay, that means P of x is going to be, I am giving this just as an example for getting an insight to the problem. Okay, there can be any number of elements in it, so it will be giving me a, b, c, just all the subsets a, b, b, c, c, a, like this, a, b, c. Okay, and also phi. Okay, so this is going to be px. Now what they do, they define a relation R in px. Because px is a set, p of x is a set, this is generally called the power set of x. If you go to class 11 sets and relations, you will be getting this is called the power set of x. So we defined a relation R in the power set of x such that for all subsets a and b in the power set of x, a is related to b, a or b, if and only if a is a subset of b. So two subsets a and b are related only if, like the two elements, we always found two elements, right? In any kind of relation we always dealt with elements. If the elements in both sets are equal, then it is going to be reflexive like this. So P of x, here see each and every element is a set. So it is given that for subsets a and b in P of x, a related to b only if a is a subset of b. Is R an equivalence relation on per set of x? Justify your answer. So it is once again not sort of, it's an easy one. So since every set is a subset of itself, a is related to a for all a that belongs to the power set of x. Can you get it? I hope you have no problem in it. So since a and a belongs to px, we can say that R is reflexive. Now if now for it to be symmetric, let us assume a or b implies a is a subset of b, but a is a subset of b does not imply that b is also a subset of a. Suppose a, it is a subset of b. Okay, does it imply b is a subset of a? No, b may be the set a itself, or b may be the superset of a. So this does not necessarily imply that b is also a subset of a. Okay, so therefore we are saying that R is not symmetric. Okay, now further, so R is reflexive, R is not symmetric. Now it is already not equivalence relation, but for our sake, for the sake of beauty, for the sake of symmetry of this problem, we are considering the transitivity case also. Now let us check it out. Further, we assume if a is related to b and b is related to c, okay, then what do we get? That a is a subset of b and b is even a subset of c. So you can see that a is a very big set, so a must be a subset of c. If a is the junior to b and b is once again a junior to c, so a is always a junior to c. So this is what this is all about. So this implies that A is a subset of C. Alright, that means that A is related to C. Okay, so therefore we can say that R is also transitive. Hence we can say that R is not an equivalence relation since it is not symmetric. Okay, so I hope you are clear up to this point. If you have any kind of doubt, please feel free to comment section, to use the comment section. I don't see any point of doubt that you may have here. Okay, anyways, moving to the next question. Now friends, coming to question number 9, it is given that a non-empty set X, consider the binary operation star, that is from Px into Px to Px, given by A star B is equal to A intersection B for all A and B in Px, where Px is the power set of X. So once again, let us now consider even a smaller example for the sake of simplicity. Let X is equal to A and B. This is the set X. Consider a non-empty set X. Okay, so we can say that power set of X is what? A, B and phi, since phi is the subset of every set. This is basically nothing. Okay, so A star B means an operation A star B that is equal to A intersection B. Okay, so since it is defined from Px cross Px to Px, every element in A and B will be lying from this Px. Okay, every element. So A and B must belong to Px. So this is clear. Now we need to show that X is the identity element for this operation, and X is the only invertible element in Px with respect to the operation star. Okay, now okay, so let us start this. So we start with the given data. It is star, it is from Px cross Px to Px, because every kind of binary operations are defined in this format, is defined as A star B is equal to A intersection B for all AB belongs to Px. Alright, I hope you get that. Now we know that A intersection X is equal to A, that is equal to X intersection A for all A that belongs to P of X. Okay, now check it out, that A intersection X, where X is the set itself, X is the set itself. If we intersect A intersection X, sorry, my pen fell down actually. So now since A intersection X is equal to A, and that is equal to X intersection A. Okay, because if we take any A, if we intersect, if we get the common between A and X, we will be obviously getting A, and that is once again is equal to X intersection A for all A belongs to Px. Thus we can say that X is the identity element for the binary operation. Okay, now to give whether it is invertible or not, means we need to show that it is invertible. So an element A that belongs to P of X is invertible if there exists B belongs to P of X such that A star B is equal to X, that is equal to B star A. Okay, A star B is equal to identity element, it must be, for it to be invertible. Now here I write as X is identity element, which I have proved in the above example element. Okay, so that is A intersection B is equal to X, that is equal to B intersection A. Alright, so this is only possible when A and B are both X, because their intersection is common, A and B. The intersection of A and B is going to be X, and that is same as B intersection A. This is X. So if X is an identity element and their intersection is X, it is only possible when A and B are both X, then their intersection is only going to be X. Else their intersection is not going to be an identity. Okay, else their intersection is not going to be this. The intersection is going to be something more than this. For their intersection to be X, this both must be equal to X. So this is only possible. This is only possible when A equal to X equal to B. Thus, X is the only invertible element in P of X with respect to star. Okay, with respect to this binary operation. Hence, it is proved. Okay, I'm sure you have no doubt this was a bit stimulating question. So if you have any doubt, use the comment section please. Coming to the next question. So we are given to find the number of all onto functions from the set 1, 2, 3 up to n to itself. Now all onto functions from this set 1, 2, 3, 4 up to n on the set of natural numbers to itself 1, 2, 3, 4. Now what here we will apply is just pure permutation and combination, if you have learned in class 11. So it's very easy. See, for a function to be onto, each and every elements of domain and range must be related to each other. So there should be no element in this codomain that should be left untouched by the element of domain. So every image, every one of the elements of domain must have one image here. So once again, let us assume any one element from this domain to be related to any one of this. Okay, so like this there are n possibilities for each of the n elements. For each of the n elements there are n possibilities to line up, okay, to be related to the codomain. So once one element got covered, suppose this, so there are n minus 1 elements, so each having once again one choice. So that will give us n into n minus 1 choices for the second element. Suppose second element is also covered. Now there are n minus 2 elements and correspondingly n minus 2 choices. So for n into n minus 1 possibilities, it will be n into n minus 1 into n minus 2, and this will be continuing. Okay, up till where there is only one element left, that is n. So n will have only one to cope out with. So n will have only one element left to link with, that will be 1. So it is n into n minus 1 into n minus 2 into n minus 3, that will be continuing up to 1, and that is equal to n factorial. This is what we are going to write in this solution. I hope the solution is clear to you, friends. So onto functions from the set 1, 2, 3, 4 up to n to itself is simply a permutation on n symbols. Okay, you get, I guess, n numbers or symbols, you may say anything. Thus we can say the total number of onto maps from 1, 2, 3 to n to itself is the same as total number of permutations on n symbols 1, 2, 3 up to n, which is n factorial. Okay, so this is the solution. I have explained here why it is n factorial. I hope you should have no doubt. If you have the basics of permutation and combinations clear, you can make it out just like that. Okay, so I think you have no doubt. If you have any kind of problems, feel free to use the comment section. I'll be trying to reach you as much as possible. From the next video, I'll be discussing from question number 11 onwards. Thank you very much for watching this video.